We first started noticing these underwater landslides when we started a systematic mapping of Lake Champlain using sonar and multibeam, which Tom alluded to last week.
We're here today. Ms. Patrick Manley is here with us, Professor Emeritus.
Patricia.
Patricia. What did I say? What did I say? Patrick. I told her when she came in, I just almost had the same shirt that she had. I put it out this one, I'm going to wear that, and I said, no, it's a little heavier shirt than I need, so I got to this one. Patricia Manley. Received her doctorate from Lamont Doherty Earth Observatory of Columbia University in marine geology and geophysics. She began teaching at Middlebury College in the fall of 1989, recently retired 2020. While at Middlebury, she routinely involved students in her research on Lake Champlain sediments, as well as, correct me if I'm wrong here now, Holocene paleoclimatic research in the North Atlantic and along the bays and fjords of Antarctica. Wow. She has served as the chair of the geology department for several years, founder of the undergraduate research office at Middlebury College, and was recently associate dean of the sciences. She has received the Association of Women Geoscientists Outstanding Educator Award, been inducted into the Vermont Academy of Science and Engineering, and is a member of the Council of Undergraduate Research at the national level. Would you please welcome Patricia Manley.
Hello. You can call me Pat. First off, thank you for inviting me and last week Tom to come and present. It's always fun to be able to present the material that you love, and Lake Champlain is one of those loves. I want to also acknowledge that a lot of the work I'm going to show you today is actually work that I did with undergraduates at Middlebury College. I've got them listed with the years that they graduated. And if it wasn't for those students, I couldn't even talk about subaqueous landslides in Lake Champlain. We first started noticing these underwater landslides when we started a systematic mapping of Lake Champlain using sonar and multibeam, which Tom alluded to last week. But before I get to that particular topic, I want to give you some background. And the first part of the talk will be about how Lake Champlain came into existence. And I can't really talk about that without you understanding something about the geologic history of Vermont and then the glacial history in Vermont. So that'll be the first part of the talk. And then the second part of the talk, we'll be talking specifically on these subaqueous landslides. So that being said, I'm going to show you two pictures here taken 100 years apart. Now, if you look closely at them, you'd sit there and you'd say, well, there's not much change. And this is 100 years. So when we think of things happening in the earth 100 years, what kind of events do you guys think about? Earthquakes. Floods, tsunamis, volcanism, all these really very catastrophic kinds of events. Well, yes, that's exactly what shaped man's understanding at first. But then we started putting geologic time into it. And what we know is it takes a long time for the Earth to change. And if you look at these two pictures besides this guy here, can everybody see the pointer? No. Okay, besides this guy right here, the only difference I've been able to discern is that there's a little rock right there that is not there anymore. Okay, so that's just the concept of time. 100 years and one little rock got put away. Well, we need to talk about geologic time And briefly, if I put it into a calendar year, here's the beginning of the Earth, 4.5 roughly billion years ago. And if we get all the way to November or December of this geologic year, this is where we start seeing fish, land plants, so forth and so on. We get to the last day of this calendar, and what we see is man shows up at about 6 p.m., okay? Ice ages, which we will talk about, is at 7. And then as you look at the very last minute and a half, what you can see is what we know and understand about our history, man's history, really happened only in about the last, say, 17 seconds. Okay? So putting that in context, the Earth has gone through many different changes in those many years, but man is only understanding a little bit of it because of our recorded history. So where do we find out about the history past that? Well, because I'm a geologist, it's in the rocks, okay? And it's the fossils in those rocks. So here is our geologic time scale. Is there a stick or something that I could use? Probably not, okay. So when we look at the very bottom of this graph, you have the Earth forming 4.5 billion years ago. And then it's broken up into these categories. This is known as the Precambrian. We don't know a lot about it at all. And then it breaks at about 540 over there, known as the start of this period, the Paleozoic. Paleozoic means ancient life. And that starts about 542 and ends at about, 250 million years. And it's during this time period where we start having the hard parts of plants and animals being recorded in the sediments and the rocks of that time period. And then the next era is the Mesozoic era. That's known as middle life. And in fact, that's the time of the dinosaurs. All right, so from 250 up to about 65 or 66 million years ago, that's the dinosaurs. And the rocks are still being deposited as well. Of course, we had the mass extinction of the dinosaurs due to the...
Climate change? Ice age?
No, not ice age yet. The big meteor, yeah, that hit the Yucatan Peninsula area. But the ice age did change a few things in this era, the Cenozoic. And so in the Cenozoic, we go from 65 all the way to present, and again, each of these time periods are given names. And you can see at the very end there where we have the humans coming into existence. So a couple of things on this particular slide. I want you to notice how the continents have changed. That's these blue things right here with time. And that is going to lead us into another discussion. So, 2 questions I hope to answer for you. How old are the rocks in Vermont? Anybody have an idea?
They're very old.
Very old, okay. Good guess. They range from 1.4 billion years ago to 350 million years. Okay, that's geologic time. And how old is Lake Champlain?
Small fraction.
Small fraction. Yeah, it's only been in existence 14,000 years. Okay, so a lot of things are happening in the Champlain Basin here. So I'm going to do a quick geologic history of Vermont. Now this is a fun picture of what the state looks like with all these different rock formations, okay? So when I say rock formations, if we scraped off all the soil and everything and you saw the bedrock, the structure that all the sediment is, works.
It's very old.
Oh, okay, yeah. So again, these colors show you different specific times and rocks associated with those times. So if you just looked at the state of Vermont, what can you tell me about the orientation of these formations? They're north-south, right? And they're like bang, 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 one right on the other. And the only early stuff we have in this area would be some of these igneous intrusions over here in the Northeast Kingdom. Okay, this star is meant to be Middlebury, and of course we're up here. So when we take a look at these particular formations, the ages of them, as I've told you, are down here. So the question is, what was happening, and how did we get a state that looks like this with rock formations? Well, that's plate tectonics. Now, how many are familiar with plate tectonics? All right, I'll just do a quick overview. How's that? So the Earth is covered by very large, rigid, but mobile plates. One way to think of it would be, I don't know, like an egg crack, a solid cracked egg. You have the little cracks, and the hard shell parts would be each one of these kinds of plates. Is that okay with everybody? Okay, so they're mobile, meaning they get to move on the surface of the Earth. And they move because underneath, down in the lower part, it's sort of like a silly putty, so it can move with heat. Anyways, that's a very trivial way of explaining it. But we have three types of plate boundaries. One is where a plate is pulling apart. One is where a plate dives down under another plate. And then one where plates slide past each other. Okay, plates that slide past each other. One of the most famous is the San Andreas Fault, okay? It is a plate boundary where there are two plates literally sliding past each other. And what do you get when you slide plates? Earthquakes. Got it. Okay, now we have plates that subduct. And usually it's the older plate will subduct underneath a younger plate. And what happens is it will melt. And it'll make volcanoes. So the Cascades in northwest US is this process. Those volcanoes there are coming because there is a small section of a plate subducting up there. The Andes, which is probably the most common one that we talk about, all this area is where these large volcanoes are making it to the surface. Not only do you get volcanism, but if I'm pushing two things past each other, you'll get earthquakes as well. So when you hear about all these large earthquakes down in South America, you're talking about this plate trying to push underneath that plate. Okay, and then the last one is rifting. Okay, so the north, this plate boundary right through here, this is the North Atlantic, down to the South Atlantic. This is a place where the two plates pull apart, and where they pull apart, molten materials coming up and making more parts to the plate. That happens mostly in your mid-ocean ridges. However, we can literally cause some kind of rifting in continents as well. Now I need to make mention of our continents. What we live on is less dense than the plates I'm talking about, and we're passive riders. So whatever way the plate's moving, that's the way the continent we're living on moves. Okay? So anyways, we can also rift continents in two. The other thing is we have very interesting sediments, and if you haven't gotten it, that I love mud and sediments, all right? We have things that are called passive margins, which would be off the east coast of the US right now. We have a plate subducting under another, causing volcanic island chains like Guam. And then, of course, underneath continents, and that would be your ring of fire. You probably have heard about the Pacific, because it's totally rimmed, mostly, with subduction zones. So you get earthquakes, and volcanoes. These passive margin sediments are what eventually is going to be Vermont. So we call this continuation of rifting a continent apart and bringing it back together a Wilson cycle. And if we put ages on the Wilson cycle, it takes about 500 million years to totally complete this cycle. So we rift a continent apart, and then we make a long linear ocean. So that would be the Gulf of California, the Red Sea. These are areas where continents are pulling apart, and we have these long linear oceans. We keep spreading them till they go as far as they can. That's the Atlantic Ocean. Then what happens? It comes back together. And these continents that have been collecting sediment, they're going to collide. And so what happens? We'll build some mountains, and then eventually go back to a big continent, and we start it all over again. How's that? Is it okay with everybody? Okay. So, passive margins form on the side of a continent that has rifted apart. And it has wonderful sediments right here. So if you go to the East Coast, anywhere, you walk out onto the sandy beaches, that kind of stuff. Well, if you keep walking out into the sandy beaches, you'll go into limestone, possibly into shales, mud, okay? And that's the material that when I start putting two plates together, that gets squished and uplifted. So, we are in this stage right now in the North Atlantic, but there have been times when the North Atlantic wasn't there. And here's one 500 million years ago. So here's where the North American continent is, and Vermont's somewhere, you know, in here. It hasn't really quite formed yet. Notice where the equator is. So the rocks that we get around here, as we will see, has that, the North American continent, remember, it will eventually do something like this. Some of the rocks we have around here formed when Vermont rocks, let's say, were near the equator. So what might you find in those? Very warm shell materials and organisms. Okay, so this is where it's rifting apart. And then, so we're way back in time. Now that ocean has rifted as far as it goes, now it's going to come back together, and it's going to form a huge continent known as Pangaea. Have you heard of Pangaea? Mm-hmm. Okay, that's all it is. It's when all the North Atlantic disappears and it comes back together and makes one huge continent. This is on the way, and if you want to see where our sediments are, you can see we have this stuff we call that passive margin stuff. And then over here, as this plate is subducting, we're scraping off mud, and that's causing sediment. And then eventually you're going to collide, and you're going to get all these different rock formations, one right after the other. So this has happened a few times on the East Coast. We've had an island arc come in and hit. We've had some other things come in and hit. You notice we're just sort of layer caking them one after another after another. And what we also have, finally, about 400 million years ago, here comes Africa. And Africa collides and makes all sorts of mountains. What mountains do you think it made? Part of the Greens, the Appalachians. So, and again, here's all those different rock types of different ages that have been plastered in a sequential way in the state of Vermont. And again, here's that collision, and the Appalachians were quite a large belt of material getting folded. And if you look right up there, we're at the very tail end of part of the Appalachians. So our green mountains are part of that material that was gathered on the side of a continent and eventually was brought up. Now we have a valley in here, and here's our mountains. So the question is, why do we have a low elevation versus high? Depends on the material that's here. And what you have is a lot of limestones and shales and sandstones, and it literally is eroded into this valley over many millions of years. Again, to look exactly at the rocks that are here, you may have heard some of these different formations, but you can see from the Cambrian to the Ordovician, we have what we call dolostone. It's limestone with a little magnesium in it. We have limestones into fossiliferous, meaning it has lots of fossils. The embedded limestones and into the shales. Now, if you go over to Crown Point area, you will find all sorts of beautiful fossils. Big snail-looking macularites. There are actually long, what do you call them? brain freeze here. Nautiloids, before they were curled, they were actually in a long shape. And you see snails and shells of all sorts of different animals, all formed in a limestone environment. So again, some of these regions you probably are familiar with. Okay, questions before I move on? Yeah?
Not much a question, but there are areas over in Grand Isle where you find these.
Mm-hmm. Yeah, exactly. And that's all part of that same limestone region. Yeah?
Where, excuse me, where and when was granite formed?
When was granite?
Where and when?
Okay, granite is the result of molten material that cools at depth through time. And then a lot of those big plutons you see, those were, the molten material came up but never made it to the surface, and then it cools. And then through what we call uplift and erosion at the top, the granite is exposed.
Okay, to further that, what's the connection between granite and marble?
Okay, granite is molten material derived from lava. Limestone, did you say?
Marble.
Marble is metamorphosed limestone. Okay, so limestone is just calcium carbonate. And with time and pressure and heat, you can transform it into something we call marble.
Okay, thank you.
Sure. Any other questions? Okay, so I've laid the groundwork for the rocks that we see around us. And since, of course, these have been laid down, our area has undergone lots of different events, right? And the main one that has really shaped our basin that we see today is the last glacial history of this region. So here we are sitting between New York and Vermont. New York is mostly, on the west side, is mostly this Precambrian, very old, hard rocks. And to the east, in the Champlain Basin area, it's mostly limestones and marbles and all those kinds of sedimentary rocks that got squished onto the sides. Okay, so about 18,000 years ago, we had the last big glacier in this region. And this is what we call the maxima. It's probably where it reached the most. And here you can see where Lake Champlain is right up there. Now, we're saying that that was the time of the last maximum, and then the climate changed and the whole thing warms up. Remember, this is the last one, which is the Laurentide ice sheet, but prior to that, we had at least 4 to 5 other major glacial advances, okay? We don't have a lot of record of those advances in Vermont because this one sort of wiped out everything. Okay, so we're going to warm up the climate, and what's going to happen is that we will have the ice go back and the land rebound. So again, thinking about it, if you have a big pile of ice sitting on something, it's going to depress. You remove the ice real quickly, it takes a while for the land to keep coming back up. Okay, so we do that, and we're going to take a look at some of the things. Again, here is one of the, image of sort of the last glaciation. Here you can see an earlier glaciation. How do we know they were there? Well, some of the materials that they leave behind tell us. And one of those is something we call a moraine. Think of these ice things as bulldozers, and they're pushing a lot of soil and rock and crap, let's just say, in front of them. And then if the ice retreats, that pile remains. And we call those, there are lots of different names, but the ones that are at the very end of a glacier are end moraines. And here you can see in Long Island and Cape Cod, those are time periods of when the glaciers were at that stage. So if it has certain things in it, you can date them. And here is a graph that sort of shows you the different stages, different moraines, as the ice was moving back up through Vermont. And what you can see is there's always this sort of tongue right through here, but when we really look at where Lake Champlain is, it was about 14,000 years ago. Okay. What happens when a glacier melts? What gets produced? Water. Okay, so here we go. Let's say the ice is down here by Brandon, and there's water in front of it. We call this a proglacial lake. Makes sense? And you can see that this proglacial lake is draining where? South through the Hudson River. Help carving the Hudson River. We move back in time and the ice retreats to the north. Well, I have more water. That means the lake has to get bigger. And this stage, known as Lake Coville, was 600 feet deep where we are today. Okay? We take it a little further back, almost up to the Canadian border. We have more water, but it now has a place to spread out. And you can notice that all of a sudden it's not draining to the south anymore, and that's because the ice in this area has been gone for a while, and that is causing the land to tilt back up slowly. Collectively, we call these different stages Lake Vermont. All right. This is just something I took when I was flying down to Patagonia to reach the research vessel. Here is the glaciers. I think you can see here's the proglacial lake. And if you watch, you can see a river going off all the way into the ocean. So this is just trying to show you how it might have looked through here. So we have this retreating Laurentine glacier, huge water in front of it. We call these various names. Here's Lake Vermont. But look what else is forming. The Great Lakes. Why do we say this is the 6th Great Lake? It formed exactly the same way at the same time. Okay, so we start moving on, and this would be the aerial extent maybe of Lake Vermont, just to give you a visual. So it's really can be high and wide. Now, the ice gets past the St. Lawrence River, and this area is going to be important later on as well. The water is draining out this way now to the ocean. Here's Lake Vermont. Well, if this is an ice edge, And this is big ice. What's it going to do to the land? Push it down. What's going to happen? What's this? The Atlantic Ocean. And it's going to come in to our basin. And it is known as the Champlain Sea. It's a brackish saltwater type of water. Notice, it does not go to the Great Lakes. This is what makes Lake Champlain so special. It doesn't have that. They don't have that history at all. Notice it also, though, is into Ontario and Quebec, and that is also going to be important as we move on. Well, it's more of a brackish water, but we do have beluga whales swimming around in the Champlain Sea. There's been several skeletons found of them. And if I have my core and I take mud, my favorite thing, I can pull out microfossils that are marine derived. Okay, so we have then the Champlain Sea. Oops, this is Lake Vermont. Champlain Sea is a little smaller. And then what we're going to see is it was draining south, but now it doesn't drain. It drains to the north. And we're going to now go into modern day Lake Champlain. Okay, so here's a basin, and I've had sediment falling down from Lake Vermont. It collects in the lows. And then I get Champlain Sea sediment, and it collects on top of Lake Vermont. And then Lake Champlain sediments collect on top of that. So there's this, what we call a stratigraphy. And because of how these lakes were, we can actually figure out what sediment we're in by whether we find these marine fossils or if we're really looking at freshwater materials. Lake Vermont was nothing. It was too cold. So now you can look where you live, and mud season's coming up, right? So the red and the purple are the Lake Vermont sediments. Very tacky, really sticky stuff. Then Champlain Sea comes in, and there's its sort of boundaries. A much nicer clay to work with. And now you can see what is left over when we go to modern day Lake Champlain. That stratigraphy is in the sediments in Lake Champlain. You can see Lake Vermont, Champlain Sea, and Lake Champlain. This is a chirp image, and we'll get to that briefly. Okay. Any questions? Okay. So part 2, these landslides. All that to get to the landslides, right? Well, it's important. So the types of things we use to understand these landslides were this unit here, we call it chirp, the multibeam, which Tom talked about last week, taking cores and dating them, so forth and so on. And this is the brand new imagery that Tom produced for me over the last week and a half of the most up-to-date bathymetry of this region. And I'm going to focus on 3 particular areas, and your map should have all of this on it. So here is profiles of chirp. Here's an animation of what that chirp might do. Not working. Oh well. The sound goes from the unit, bounces down into the sediment, back up, and it reflects off of specific density changes. Well, there's modern day Lake Champlain, there's Champlain Sea, there's Lake Vermont, all different densities. And so we can actually trace these packets, if you want to think about it, throughout the lake. And then Tom already talked about the multibeam, where you actually have large not going to do it, large transducers, 512, that as you go along your ship, moves, you get depths, 500 places, And they all come back up and you can make a bathymetry map of the area. So, and then piston coring. Piston coring, here's our piston core here. It looks a little different than this one, but we have a weight at the top, we have a trigger arm, we have extra wire here, and then a plastic tube within a metal tube. And as we drop it, this hits the bottom, releases the arm, and this thing free falls, just right to the bottom. And as it does that, it collects sediment in the order that it has been collecting. I do all sorts of things with my mud, and this is a lot of the stuff that I will be talking about. And down here you can actually see a small section of the core with some laminations in it. Okay, so landslides. Here's a cartoon. You can see that it always falls on a ruptured surface. They can sometimes have a block that's still intact and then the rest of it goes out. Well, here's a chirp profile. Once again, this is the sediment water. And now you're looking below the surface at these sediments that have been accumulating. I can tell you that when you see this kind of pattern, that's Champlain Sea sediments. And this stuff here is pure rock. You don't want to hit it with a core. Okay, well, Tom's oceanography class actually found this. And a few years later, we decided to take a core right here. So as I said, this is Champlain Sea stuff, right? And that was stopped, what, 9,000 years ago. So there is no way that a sediment falling now on that surface is going to be Champlain Sea. It's going to be Lake Champlain sediments. Does everybody see that? Okay. Take a core, and what we found out was there was at least 10 centimeters, which isn't a lot, of Lake Champlain sediments on top of that interface with the Champlain Sea. We actually know sort of the sedimentation rate, and we calculated that it probably failed between 1875 and 1880, roughly, okay? We can't get precise. But what happened in 1870 was a very large earthquake in the Charlevoix area in Quebec. This is the first time we thought about what might be happening if there's large earthquakes up to the north, to the sediments in Lake Champlain. Another way to display disturbed sediments, again, this one's consistent, no blocks, but it comes out in this nice big lobe. We call it a debris fan. Here's off of the west coast of the United States. This is from Middlebury. And again, you can see these beautiful lobes, right? Hey, look at Lake Champlain. We got a lobe here. We have a lobe there. We have a lobe up right here. And lots of lobes down here. All of that suggesting underwater landslides. Okay. Again, these are just images of the various slumps or mass wasting. Here you can actually see the scarp face on that one. This one isn't as intense, and this one is more like think of a slug of material just slowly going down the slope, right? But they're all mass movement of material. Is it fast? Is it slow? What can we say about this? So what I proposed with my students over these past few years is there a common failure surface? What is the age of maybe these failures? And what is the causal mechanism? So if I can answer those three questions, we'll have a handle on it. So this is a slump right here. It's the Four Brothers. It's just south of Four Brothers Island. You can see the beautiful debris land, right? You can see these on your maps as well. We took a core right here, and one of the key things we use is magnetic susceptibility on the core. All it is how much magnetic material is in it, okay? But we do know that every time we have a large flux of magnetic material, that usually means you're going from Lake Champlain to Champlain Sea sediments. And we could talk later about that if that's an interest. Not only that, guess what I found at the bottom of the core? Nice E-clavatum. So what we know then is this is all Champlain Sea. This is Lake Champlain. And so the question is that where is the failure surface? Well, this surface right here is the Lake Champlain, Champlain Sea, and you can follow that thing all the way up. We needed to know its age, so we took another core and we did all sorts of dating techniques, led to 10 concentrations of cesium, which we know peaked when we had above ground nuclear tests out west. We know roughly the age that is, kind of thing. We also looked at how the magnetic minerals in it were oriented, and we basically could come up with a rough idea of, again, sedimentation rate. Okay, so if I have a sedimentation rate and I know what that thickness is, I can get an age. Now, why am I pointing to that? Notice there's laminations above that area. It's where we went from Lake Champlain to Champlain Sea sediments. So that's the material that collected after the failure. Doing that, we come up again with an average range of time periods that this particular slump, I call them slump and debris flows, that all means the same thing, sorry, is about 4870 years before present. Okay, so if we go up to Quaker Shoals, this is way up here east of Four Brothers. Again, wonderful debris fans, and I don't think this is going to work, is it? Maybe. This is a rendition that Tom did where you're going to see it, we're going to rotate around. And I want you to notice you can see the scarp really well. So that's the area that failed, and it all came out here. And the same thing with the north area, you can see the scarp as well. We do the same things. We take seismics, we take cores, we do all the analysis that we can. We know here is Lake Champlain, and you can see the failure surface. Here's the magnetic susceptibility. It jumps up. That's the interface between present day and when it failed. And doing, again, all those different sedimentation rates and stuff, we have found that we have some ages we can associate with those. Okay. Now we're going to go down to this region in the very bottom, and you can see there are tons of these underwater landslides. And this was work that was done by my one student, Perry, where she looked at, you can almost see over here how where the material has failed. Look, this material hasn't failed, and this material hasn't failed, but it has in between. So to do that work, it's a little hard because it had not one, but several places where it seemed to fail. And so looking at a line that goes from north to south, that's this one, you can see, for example, this has never failed, and this has never failed. And if you could look even closely, there's a little bit right here and a little bit right there. And how we approached it was that we, again, took cores to get a sedimentation rate, so we could then start quantifying it. And what we did was, using our chirp seismics, we measured the thickness between when it failed and that interface right there. We did it in all of these situations. I can tell you because of the cores that we took, this strong reflector right there and here is the transition into Champlain Sea. So she came up again with failure dates as well. So how does that look? Well, if you look at just Perry's work, all three of her big debris flows almost are the same in age. And she had one that was only about 1,000 years ago. If we put on the Quaker stuff, which was to the north, and the Four Brothers, they are what we would call coeval. In other words, knowing that our ages are going to have some, I don't want to say slop, that's the wrong word, but some variations, we are saying that these all failed at the same time. So what is that failure surface? So I had another student who went and took course and looked exactly at the failure surface. Here again is magnetic susceptibility, and there you can see when it goes up into the Champlain Sea. So he looked and tested material above the failure surface, below the failure surface, and then a slight range within the failure surface. And he did all sorts of geotechnical tests. Basically, we're looking for these different limits of whether a material acts as a liquid or a plastic. And we needed water content, so we took water content. And this is probably, I think this is hilarious, but this is one of the most sophisticated pieces of equipment we used. This is called a Casa Grande test. And what happens is you put your mud in there, you put a sort of a gouge in the center, and when you rotate the thing, you count the number of times the little cup drops. And when the two pieces come back together, you plot that versus moisture content, and then you look at the intersect at 25 drops, and you come up with this liquid limit. It's a test that's used all the time. Now your plastic limit, you basically sit there and you take some of the mud and you keep rolling it like Play-Doh until it fails. Okay, and so that's another way geotechnical test that's used. The main gist of this is we're looking at the liquid index. The liquidity index, if it's greater than 1, it's sensitive to disturbance, but doesn't mean it necessarily will. If it's really less, it'll behave plastically or fail. And again, here's the interface sediments, and what we're seeing is below, it's pretty tough stuff. And above, it's also going to be sensitive to disturbance, but doesn't necessarily mean it's going to. And then in this interface, you can see that we have very large values, which say, this area could actually fail. Putting it in perspective, again, Lake Champlain sediments have the highest liquid limit, highest plastic limit. Below was the lowest, but in the intermediate, it's sort of all over the place. So basically what that's telling us is that it's this interface that seems to be failing. Why? Okay, Champlain Sea sediments are a nice dense clay. You saw the magnetic susceptibility go up. Well, I could show you density, it also goes up. So you have water percolating down through Lake Champlain, and then it hits that sort of boundary. So what happens to the water? Well, it sort of collects there. It can move laterally, I'm not saying it can't, but it's at that interface that causes the problems. What are the triggers? Okay. Well, Tom's already talked about tidal changes don't exist, wave loading because of these being very deep beyond the wave base. There's no gas, we can tell that from our seismics. There's no failure of sediment below. what's left is seismic or decrease of friction along an impenetrable surface. And these are just showing you the various earthquakes, and the circle size is bigger and bigger magnitudes. So, interestingly enough, in May 11th, 2010, huge slide happened up in St. Jude, and it literally fell along the surface of the interface between modern sedimentation and the Champlain Sea stuff. Anyways, notice where that is. It's when Lake Champlain was there. So trying to put this all together, what we can see is that we have, excuse me, go back, work that was done up in this area by Greg Brooks showed there were 2 dominant times of earthquakes and landslides up in that area. Notice they're around 5,000 and 1,000. If you look at our data, around 5,000 and 1,000. So what we're thinking is that it's got to be earthquake-driven time period that caused a lot of these failures. So is there a common failure surface?
Yes.
And it is the interface between Lake Champlain, Champlain Sea. What are the ages of failure? Well, I just told you those. And what is the causal mechanism? Well, we believe it is got to be earthquakes occurring up in the western Quebec seismic zone or the Charlevoix area. This is an article in 1820 which talks about a piece of land that fell into the lake, and it generated a surface wave that basically raised the water at least 3 feet on the opposite side. Okay, so that's understandable. A clump of land goes into the water, it makes a nice big wave. Well, what happens if we have these underwater landslides? What happens to the water? If you have material here, and all of a sudden it's here, what happens to the surface of the water? It goes down and generates a wave that we call a lake tsunami. So Tom worked with these, and we generated this model. Hello. And what you're going to see is the failure of the 2 in the north here and 4 Brothers. We have yet to put in the Essex side. But what you're going to see is the initial earthquake, the drop of the water. Notice how the waves are going along. This is a lake tsunami. It's going to play again. But notice where, in this case, where it heads. It heads into Shelburne and Burlington Bay. Now what you should notice is that this means 4 meters above the present day surface, 4 meters below. So when it first happens, the water drops, rebounds, and then sends out, this pattern continually. So if we take a look, just not even 3 minutes after the earthquake, here's that bottom drop, the wave. Here's the surface of the wave as it's coming in. And what's in its way? Shelburne Point. And it's literally going to hit Shelburne Point 3 minutes after this particular earthquake. So, we haven't done it with these debris flows, which I've talked about. But one of the things we wanted you to understand is there are lots of unfailed surfaces or areas of high sedimentation that still exist. And should we have another large earthquake up in Quebec area, we have the potential for, again, sort of a mass amount of land going down into the lake and possibly causing a lake tsunami. So, just to conclude, 2 periods of mass wasting, failure along the Champlain water interface. At least 6 of these mass wastings we've tied together in a particular area. And then using the COMCAT model of Cornell, we tried to model what it might happen to get a lake tsunami. And eventually what we have is that we need to think about the future about large earthquakes and underwater landslides. And these are the crew. This is Brandon and Piper and Jaya and Perry that all did the work for this particular talk. Thank you. Yeah.
We had an earthquake, I don't know, maybe 10, 15 years ago. It's kind of over on the
Plattsburgh area.
west side
Yeah.
of the- Is that,
Well, there's a couple things. One, it wasn't large enough. The earthquakes we're talking about that have triggered a lot of these surface landslides as well, what we think are happening down in the water, are on the order of 7 to 9 in magnitude. So very large ones. I think that one was maybe a 5.5 or something. And also it was in this old Precambrian rock stuff, which doesn't transmit as well. Earthquakes, waves transmit and amplify if you're in sort of looser soil areas. So that's probably why we didn't see any effect really over here, other than maybe feeling it.
Do you have any sensors in the lake that would notify you if there was a slide that you could get there quick and get?
No. No, not at all. Yes?
Okay, so forgive the scatterbrained nature of this question, but is it safe to assume that 300,000 years is enough biological time to impact the ability for like Homo sapiens to travel certain areas?
Okay, so, well, really, yes, the main thing is where what we call the land bridges are. So remember talking about how the continents move around. Well, also along with all of that, our oceans. If I have a glacial time period, where's all the water going? It goes into the ice, which lowers the ocean levels and exposes areas for animals and primitive people to migrate around.
So over the course of 300,000 years, it could reasonably have affected change if someone was to otherwise cross a path that couldn't be crossed?
Yeah.
Okay, so what I was able to infer from this, and tell me what you think, you might appreciate this. If military strategy, the #1 thing is geography, and what we get as humans from a whole life of military and global conflict is the advancements of technology and commerce. If over 300,000 years there's been enough change to affect where people are, then where we are on the timeline, somehow you could infer that if a earthquake didn't happen 300,000 years ago, it would change where we place strategic points in the military. And if that leads to technology, then maybe we wouldn't have televisions if an earthquake didn't happen 300,000 years ago.
Oh, interesting. Well, I think one of the ones that I always wonder about is the Fukushima nuclear disaster in Japan. Well, that was a subduction zone, and instead of building the plant on the western side of the island, they built it on the eastern side, where the tsunami, because of the subduction, could come in and wipe it right out.
wow.
So knowing those kinds of things, that's more like where should we put certain things? Yeah.
Can I go back to part 1 a minute? And this is a short answer on a long question. What's your take on global warming?
Oh, it's happening.
That was a short answer. Is it here to stay? Is it a cyclic thing, or?
Oh, there's so many different concepts and ideas floating around there. One of the things they've talked about is with the glaciers melting in the North Atlantic, it's going to come out and shut off what we call the global conveyor belt of the ocean system. I just read recently that models are showing, no, that's not going to happen. So it really is getting back to what Tom had said last week. You know, the models are only as good as what you can put into them. And our climate record is very limited in time. So having been in...
100 years is a long time.
Yeah, but where do we get the record? Where is that preserved? Is it in the ocean deep sediments? Is it in tree rings? I mean, that's the problem there. I've been working in Antarctica doing that kind of stuff, and we take these 50-meter cores to try to answer those kind of questions. And I can tell you that the work I've been associated with down there does show that our oceans are warming, and they are affecting the ice shelves. You've probably heard a couple of them have collapsed, and that's because the warmer ocean waters are coming underneath them. And
We know why, but is it the first time that it's ever happened?
oh, heavens, no, climate's changed.
So it's cyclic?
No.
No?
No.
Could be.
Okay, on a grand scale, you have something called, this Milankovitch cycles, which is how the sun, moon, and earth are interacting through time. And we have periods of about 80,000 years of the conditions of the orientation of the earth and the sun, which will allow glaciers to grow. And then we have 20,000 years where it's not. Well, where do you grow glaciers? You have to have continents somewhere. They have to have high elevations. I mean, you can see it's a very complex thing. And yes, we have some climate signals that way. The glacial advances and retreats are very much related to that cycle. But back in time, it's hard to say.
Thank you.
I hope that answered your question.